It is January 1973 and NASA has just cancelled a project. The space race is over and money is getting tight. The project on the shopping block is a fascinating propulsion system. The project had run since the 1950s, and being peak nuclear age, of course the project was atomic in nature. The project that was being taken out behind the barn to be put out of its misery was the nuclear propulsion project. But our story today will be more focused on just one part of this, and that was around 10 years before its cancellation. That is the destruction testing of a nuclear reactor, in what seems to be a bit of a tradition during the age in the USA. Personally, it's my favourite part of this period of history, back when destroying a reactor for the crack of it was just a normal part of any type of nuclear reactor development. And it yields this brilliant photograph of a nuclear reactor tearing itself apart, like a 1980s action hero rips his t-shirt. Today we're looking at the Kiwi Transient Nuclear Test. My name is John and welcome to Plainly Difficult. Today's video wouldn't have been possible if it wasn't for my Patreon, YouTube and Ko-fi members. If you want early access and ad-free access to the channel's videos, then you can from just £1 per month. And as always, the link will be in the pinned comment below. Harnessing power to the stars. Harnessing nuclear power was post-World War II at the forefront of many different industries. The obvious ones of nuclear reactors for producing nuclear weapons material and the other for generating almost endless electrical power. This got a lot of attention from the powers that be, but other concepts for the use of nuclear power were also entertained, in the never-ending battle to get one up on the pesky Reds. During this period, nuclear-powered aircraft, trains and automobiles were vomited out of the minds of scientists. Most of these ideas faltered at the design stage, although a serious crack in nuclear-powered planes was attempted. I do have a video on that, a rather old video. One such idea was a nuclear-powered rocket. It gained some traction. This in the 1950s were a fearful time, and the need to get bombs as far as possible spurned on the early days of a thermal nuclear rocket project. Because you see, a rocket is very, very good at delivering a payload, most notably a nuclear bomb, over a long distance. Now the concept for a nuclear powered rocket is beautifully simple. Instead of using chemical heat from burning propellants, it uses heat from a nuclear reaction. Don't worry, I'll go a little bit deeper into this a bit later on in the video. The original plans for a nuclear-powered rocket under the US Air Force and the Armed Forces Special Weapons Project was transferred over to NASA after it was deemed that the Atlas missile project was looking like a good platform for Soviet annihilation in 1957. Spurned on by the Sputnik scare, NASA and the Atomic Energy Commission joined up to form Project Rover. The first stage of the project was to design and build a working reactor rocket motor. This would be given the name Kiwi A. The reactor was a proof of concept and not actually intended for flight, thus being given the name of a flightless bird. Now, I've skipped past a lot of information on the ins and outs of the decisions leading up to the first proof of concept, but we're here for a nuclear reactor explosion and not the inner workings of US defence policies of the 1950s and 1960s. Anywho's, Kiwi A ran between July 1959 and October 1960 over 3 test units. So the Kiwi-powered rocket proved rather well the concept of a nuclear engine. So let's look at how it worked. It was a solid core fusion reactor. The core employed a graphite moderator loaded with highly enriched uranium-235. A propellant of hydrogen is passed through the reactor core via a feed pump from a propellant tank. The hydrogen doubles up as the reactor's coolant as well. The fission reaction is controlled by actuated control drums which had neutron absorbing material on the face of it. If the drum is turned away from the face of the core, the power is increased, and conversely, when turned towards the core, the power is lowered via neutron absorption. The high heat from the fission heats up the hydrogen, and the high heat gas expelled out of the nozzle at the rear of the engine produces thrust. Nuclear reactor rocket engines are beneficial in comparison to conventional rocket engines, as noted by NASA. Nuclear thermal propulsion provides high thrust at twice the propellant efficiency of chemical rockets. freeing up weight and mass for payload and mission essential supplies aboard the spacecraft. But they do come with a downside, that is, that the exhaust out of the engine is radioactive. Thus they are better suited for travel away from humans, like in the later stage of a rocket launch. So Kiwi A proved the concept, generating a thermal output of 70 megawatts at an exhaust temperature of 2683 Kelvin, and further developed the program. Next came Kiwi B. This brought about greater power outputs, but new issues in the cases of vibration and heat damage. Although development issues were found, the project was deemed successful enough to warrant the next set of tests, and this was safety tests. Kiwi TNT. As a flight-ready engine became more and more likely, the risk of an accident involving one crashing back to Earth had to be assessed. What better way to do this than to deliberately destroy a reactor? Scientists wanted to recreate a scenario as stated by NASA. Might happen if a chemical rocket booster aborted and dropped a non-critical nuclear reactor into the ocean, where the water, being a good neutron moderator, would increase the likelihood of fissions and could make the reactor go critical very quickly. Other safety tests were conducted around the same time, which included water submersion of core samples, but we won't go too much into that today. The destructive test was decided to be undertaken at the Nuclear Rocket Development Station in Jackass Flats, Nevada, where the other Kiwi rocket tests were done. A Kiwi reactor was modified for the experiment. This involved souping up the moderator cylinders to be turned face and not facing the core quickly. This allowed spikes in power within the core. The configuration of the core was near criticality even when the control drums were facing and thus poisoning the core. In order to allow for workers to prepare for the test, extra neutron absorbing plates were inserted into the core. This meant that once the plates were removed and turning of the absorbing control drums away from the core would cause a transient spike of criticality, thus in theory cause a power excursion that would be hot enough to vaporise parts of the reactor core, making a very big bang. The propellant supply was removed, and instead of the nozzle for high temperature gases, a mirror was placed to aid in core photography. The entire reactor assembly was mounted on a railway car specially constructed for the test. They knew there would be radiation and material release from the intentional reactor deconstruction. Because of this, extensive air monitoring equipment was employed. On top of that, monitoring of the energy release from the test was set up in an extended arc from the test site out to around 50 miles. 2 B-47C aircraft were employed to track any radiation clouds at longer distances, in addition to a U-3A aircraft that was employed to monitor radiation direction. Now, much like the borax destruction test, the weather would be vital to the experiment. Wind direction and speed were required to come in from the northeast direction, as to push the radioactive effluents towards the Death Valley. The test was planned for early 1965, as the Kiwi B test came to an end, and the morning of January 12, 1965 was looking to have the ideal weather for the test. 2 hours before the experiment, almost everyone was evacuated from the test site, apart from a few operators who operated the key locks to enable the control drums to be remotely controlled. Control was handed over to the central control room, and after the final remaining staff left the test site, the countdown began. Cameras focused in on the reactor. Then, at the end of the countdown, operators actuated the control drums, and then in an instant, criticality was increased within the core, blowing the vessel to pieces. The nuclear excursion ended as the reactor became not together anymore. The railcar assembly that the reactor sat upon was split in half. A bright yellow explosion shot out, followed by a radioactive cloud with an estimated radioactivity of 1.6 megacuries, or 59 petabecquerels. The most common radionuclides released were cesium-138, strontium-92, iodine-134, zirconium-97, and krypton-88. The explosion created a debris field including damaged uranium fuel, graphite, and beryllium, which was cleared for initial evaluation at a distance of 400 feet just 10 minutes after the test. After the dose rates dropped, recovery of recording devices and debris was undertaken. Shrapnel damage from the reactor was over a relatively small area of between 100 and 200 feet. It was determined that at distances up to 450 feet from the centre would have yielded deadly radiation doses, but 1200 feet and beyond would yield not much more than the recommended average daily dose of radiation. Film badge dosimeters had been given to people living on the edge of the test area, and milk samples from dairy farms in the cloud's path were taken, and the results were that the exposure amounts were pretty minimal. The aftermath. The test yielded some vital information as to how a nuclear-powered rocket would react to a criticality event. The test site was cleared and recovered for reuse in just 6 days after the test. The explosion did little damage beyond dislodging a few temporary metal outhouse buildings. What of the project as a whole though? Well, the lessons learned from Kiwi helped out in the development of the Nerva engine, but sadly a nuclear rocket was never launched. Even though a plan for a nuclear-powered shuttle was laid out in 1970, the newly elected Nixon government from 1969 sought out to cut back on federal spending, and the money hole of a nuclear rocket program looked like the fat to be cut. The program would limp on with a reduced budget until its cancellation on the 5th of January 1973, even though a small Nerva engine was close to flight testing. The concept still lingers on today, with the ESA releasing a study in the 2020s, and as late as 2023, NASA and DARPA announcing a partnership to demonstrate an NTR engine in space. This year, a nuclear rocket would be a vital cog in any manned mission to Mars, allowing for lower weights of propellant and more reliable engine starting that a theoretical nuclear rocket engine could provide. So today, the scale will be only at a 1. And this is what I've got for my rather empty root cause analysis card. As well, the destruction and the aftermath was pretty much all part of the plan. This is a Plainly Thought production. All videos on the channel are Creative Commons Attribution Share Alike licensed. Plainly Thought videos are produced by me, John, in a currently quite cold corner of southern London, UK. And all I have to say is thank you very much for watching, and Mr. Music, play us out please.